Hey everyone, we're going to be looking at electromagnetic waves. So let's go ahead and explain the electromagnetic spectrum as well as a couple other things. So starting off with this equation right here, C equals lambda times F. So C is the speed of light. It's actually 3 times 10 to the 8th meters per second. So C is just another symbol for velocity. It's just the velocity of light. And that is actually the highest speed that anything can travel at. So importantly, we have it in meters per second. So our wavelength, it's the length, it's going to be measured in meters. And our frequency is in hertz or inverse seconds. So that's where we get meters per second from. Okay, and looking at our rectangle right here, this is going to be our spectrum. So as we can see by this arrow right here, as we're going to the left, the waves are getting longer. So wavelength and frequency are inversely proportional. So as the wavelength gets bigger, the frequency gets lower. So that's what we have right here. A long or high wavelength corresponds to a low frequency. So at the very far end, we have radio waves. Okay. And then next, we have microwaves. So slightly bigger frequency, slightly smaller wavelength compared to the radio waves. Next, okay, actually we're going to skip this section right here, and we're going to go to this tiny little section right here. So at this point, this is going to be the visible light part of the spectrum. So the way that is explained is through Roy G. Biv, something that we've known for a long time. So at this low end right here, where we have a long wavelength, we have red. So preceding this, what do you think is going to be right here? Preceding it will be infrared light. So typically, red is around 740 nanometers, okay? And then compared to the other side, we have violet, which is around 380 nanometers. So as we go from left to right, the wavelength is decreasing, but the frequency is increasing, as we can see right here. And as we get past violet, what do you think will be in this section? And that will be ultraviolet light. Okay. After that, we have X-rays, right? Very useful for medicine. Next, we even have gamma rays, very, very high frequency. And it's actually another medical application called the gamma knife. And so yeah, towards the end where gamma rays are, we have very short wavelength, high frequency. Soon enough, it'll be important that we know that energy is proportional to frequency. So the higher the frequency is, the higher the energy is, which does make sense. You know, X-rays, you don't want to be in X-rays for too long, or even gamma rays for too long, because it's very damaging. Those high frequency waves can be very damaging. They have a lot of energy. Okay, so this is the spectrum for electromagnetic light, and let's actually look what an electromagnetic wave is. So I have this graph right here, and I'm going to do my best to draw what is happening. So this is the oscillation of the electric field, so the electromagnetic waves. Let's fill this in like this. And next, let's draw how the magnetic field will oscillate. The rule is that the magnetic field and the electric field always have to be 90 degrees perpendicular to one another. So to draw this, it might be a little difficult, but this is kind of what we have going on. Hopefully you can tell that they are 90 degrees to one another, right? So the electric field is going up and down. The magnetic field is coming out and in. And the direction of the wave propagation, that's just the direction that the wave is actually traveling. So that's what we mean when we're talking about electromagnetic waves. And this is light. We're referencing light here. So we'll see in the future that light, it acts as both a particle. So if you've ever heard of a photon, that's like a light particle. But it also acts as a wave, which we can see with electromagnetic waves. All right, thank you for watching.